this problem is such a fun problem to solve that I actually decided to bring it on the quote-unquote table and give it a go, a proper go. All right, this circuit was presented by Engineered Math random problem number 10, and that was December 11 that I got it on Facebook. Please visit that profile and give it a due credit that they actually deserve, because this is an awesome problem to solve. All right, so here's the circuit, and the challenge is to find the current I, which is this one, given the forward voltage across the diodes is 0.7 volts. It's never exactly 0.7 volts, but this is just to make things simpler, I suppose. All right, so I've connected that actually on the multisim. I multisimmed it, and we're going to go along and verify my calculations, because imagine the truth that even I'm not perfect. Yeah, okay. All right, so here's the circuit. Let's bring it up. I brought it in Photoshop. Here is that circuit that we have here. Center it up a little bit. Okay, so we have all the due credits. We can get rid of the headlines here. Okay, so here is the circuit. Let's make it a little simpler by redrawing it. So I just redrew this thing just like this here. All right. Now we have a little bit better visual on the vertical kind of granularity of this circuit. All right, so we have plus 10 volts. We have negative 5 volts on the bottom. First things first. Let's see if there's a current here at all. All right. So first thing, when we go from the top to the bottom, we meet this diode right here, and they are not labeled, those diodes, and the parts are not labeled, so I'm just going to call this and that. All right, so that's fine. So this diode right here, let's see if this diode actually conducts or not. If it doesn't conduct, then we can just throw it out of the circuit and ignore it. First thing, what voltage do we have here? What kind of, can we use the voltage divider? We have a diode. Is this diode going to conduct? Well, let's see here. There's a plus, and it just goes to -5. This diode is forward biased. Yes, it is going to conduct. So we can redraw it like this. See that? Since we have that here. In this particular situation, it is assumed that the voltage drop across the diodes is 0.7 volts. So we can just get rid of that diode, and we have 9.3 volts right here. Let's redraw it, make it more visually easy to look at. All right. So we have 9.3 volts. We're trying to see if this diode conducts or not. Can we throw this thing out of the circuit? By the means of voltage divider. What do we have here? We have 2 kilo ohms, 6, and 9. We can do it a couple different ways. We can calculate total current, and then based on that, we can calculate the voltage drop of this resistor, and then subtract that from that. What can we do? We can do a voltage divider. So let's do the voltage divider thing. So what do we have is we do have 2 kilo ohms against 9 kilo ohms, because 2 plus 6 plus 1, that's going to give us a 9 kilo ohms of total. That means I'm just going to make that diode kind of almost disappear. So we are out of that circuit. Just see what, without that diode, what this point is going to sit at as far as voltage. All right. So what we have here is 2 divided by 9. So let's do that. 2, which is that resistor here, I'll skip the kilos, divided by 9 kilos is going to give us, well, the voltage drop across this resistor divided by the total voltage from here to here, and I'm just going to draw the line here. From here to here, voltage equals 9 plus 5, because whole total voltage difference. So this voltage is 14.3, right? So 14.3, that's where it comes from. So what's the voltage drop equal to? It equals to, and I'm going to write this down. I don't like it with especially engineers. They skip the steps when explaining things. So let's not skip any steps. 14.3 times 2, times 2, that times that over that, divided by 9. 3.2 volts. So that's the voltage drop across this resistor. So this resistor is biased in a way that this is more positive side than that side. So we're going to get this voltage right here. Voltage, whatever we can call it, voltage 1. So that voltage 1 equals 9.3 minus that voltage drop, 3.2. All right, 6.12, which is this voltage right here. So we have 6 point something, whatever it is, on this side of the diode, and we have 5 volts on this side of the diode. This diode is reverse polarized. We can just throw that out. All right, so now we have ended up with this circuit. Now, is this diode conducting? Because the question is what the current is here. Well, if the diode conducts, we're going to have some value. If this diode is forward biased, which means this voltage has to be greater than that voltage. So we know what this one is sitting at. This is sitting at 0. So this has to be at least minus 0.7 volts if this diode is disconnected. So let's just pretend that we don't have that diode here. And let's see what the voltage is at this point. By the same voltage divider principle, 1 kilo to 9 kilo is same as this voltage drop, which is going to be, in our case, we just call it X, to what? 14.3. Still have 14.3. 14.3. What's the X? X equals 14.3 times 1, multiplied diagonally and divided by what's left. Divided by 9. What do we get? 1.6 volts of a voltage drop across this resistor. But how is that 1.6 volt how is that going to appear at this point? What is going to cause that point to be if this diode is disconnected? So which way does the current flow? From here, this is the more positive side of the whole series of resistors, and this is the most negative. So the current is going to flow this way. All right, cool. Which this is going to be positive side, and this is going to be the negative side of the resistor. And what do we have? What do we get? That calculation of the voltage drop, let's say 1.59. All right. So minus 5 plus 1.59. All right. All right, minus 5 plus 1.59 That gives us minus 3.41 volts right here. Minus 3 point something, whatever it is. Which means that this diode is forward biased. All right. And that's before we connect the diode. So what does this tell us here? Now, that tells us if the voltage is forward biased, the voltage across this is going to be, or it is, 0.7 volts. Which means that this puts a completely different paint job on things, because since this diode is not connected, this is what we have, like minus 3, which is lower than 0, which means the diode conducts, which means that automatically we're going to have minus 0.7 volts here. With reference to ground, what is the voltage drop across this resistor now when the diode is connected? The difference between those potentials gives us 4.3 volts, and it's this way here across this resistor. I equals V over R. So calculating this current here, and that gives us 4.3 divided by 1 kilo ohms equals this current here is 4.3 milliamps. What is the voltage drop between this point and that point? So 9.3 plus 0.7, because we're going down 9.3 volts, we have to go down more, 0.7 volts to this thing. So look at this, between here and here, we have 10 volts across 8 kilo ohms. What's the current? So this I2. Let's go I2. Okay, I2. And that was let's just call it that I1, which is that one here across the resistor, 1 kilo ohms. I2 equals 10 volts divided by these two here, which is 8 kilo ohms, right? That's 1.25 milliamps. So over here, I2 equals 1.25 milliamps. All right. So the current here flows this way, comes into this node. Once the current leaves this node is this much. Well, the rest of that must be coming from here. Otherwise, Mr. Kirchhoff was wrong. So let's see what the difference is. That I that we're looking for equals this 4.3 milliamps, like here, 4.3 milliamps minus 1.25. 3.05 milliamps, and that is our answer. I equals 3.05 milliamps, and let's just put that in a square bracket and frame that. Here's our voltage probes. Here's our current probes. Turn that on. Boom, put it there. 3.06 milliamps. A beautiful problem to solve. It has many layers of thinking involved, and there's so many traps that you can step into and cause the chain reaction of making a mistake, which is going to trip over or trip the whole final result. Thank you, Mr. Let's just get the headline here. All right, thank you, Mr. Engineered Math. Let me zoom this thing here. All right. Thank you, Mr. Engineered Math on Facebook. That was an awesome problem. All right.